Okay, thank you very much, and let me also thank the organizers for giving me the opportunity to speak here at this very nice conference. So my talk is supposed to be a survey talk. I will not give proofs or go into detail with the proofs, but rather explain the results and the context and some applications. So after an introduction, I will mainly talk about two topics. One is Cobordism groups from the perspective of SKK-relations, and the second topic will be index constraints. So let me right away start with what is the talk about. So let's consider a Morse function f on a closed-oriented n-manifold M. So the manifolds will be supposed to be smooth, differentiable of class C infinity throughout my talk, and maps will also be considered to be differentiable. And our goal is to define a Cobordism relation for such Morse functions by using the theory of fold maps, which comes in naturally, as you will see in a moment. So given two Morse functions f0 and f1 on such manifolds m0 and m1, our purpose is to define a notion of Cobordism. And a Cobordism from f0 to f1 will be a pair wf as follows. So w is supposed to be an oriented Cobordism from m0 to m1. So I suppose orientability here. You could also define an unoriented version, but let's stay with the oriented manifolds for simplicity. So this is just an oriented Cobordism from m0 to m1 in the sense of algebraic topology, or differential topology. And big F is supposed to be a map from W basically to the plane, such that the behavior near the boundaries is as follows. So if you restrict F to a tubular neighborhood of M0 within W, then it should be the product of the identity on the interval with the Morse function F0. And on the other side, in a similar way, the restriction of F to a tubular neighborhood of M1 in W, let's say a color, if it's a color, is also of this form. It's a product of the identity with the Morse function F1. And the main property is now that we also require the restriction of F to the interior of W to be a fold map. So what is a fold map? You can define it like this. One way to define it is like this. Every singular point of this differentiable map is required to have the following normal form. By normal form, I mean you must be able to pick coordinate charts around the singular point and its target, the plane, in which F takes the following form. So an n plus 1 tuple of coordinates, say x1 to xn, will be mapped to a pair which is built as follows. So the first component is just the projection to the first coordinate, x0. And in the second component, you take a standard quadratic form in n variables, which are the coordinates x1 to xn. So, in other words, you can think of this locally as a family of Morse functions, because this is also up to a constant the local normal form of the Morse function. And, well, for that reason, you see in the picture here, the singular locus of F is depicted as those red lines within W. So it's a one-dimensional subspace, closed as a subspace and a one-dimensional manifold. And if you restrict big F to this one-dimensional lines, then you get an immersion into the plane. So in the picture you see it's even an embedding, but in general there can be self-intersections. So what you can say, this restriction will be an embedding. And now this kind of notion, this notion of Cobordism turns out to be an equivalence relation, okay? So you can consider the corresponding Cobordism group of Morse functions on closed n-manifolds. And the important question that arises is now how to study this. One possible way to study is a general approach via stable homotopy theory. So you can embed this kind of notion in a more general theory where you consider cobordisms of differentiable maps with prescribed types of singularities. And then, I mean, this goes back to René Thom. He made a pioneer work in this area when he considered cobordism groups of manifolds, because in his work they were embedded into some Euclidean space, and embeddings are basically differentiable maps without singularities. And if you broaden the picture and include singularities, then you can extend the theory, and some basic work has been done by Imani and Chich, and later people generalized this more. People like Ando and Sadikov and others. So this approach via homotopy theory, via stable homotopy theory, like the Pontryagin and Thom construction, is not what we will take here. Here we will do it with more topological, geometrical methods. So let's see. The oriented cobordism group of Morse functions has been understood. So the structure is as follows. Consider again the Morse function f, and we define the following notation. Mu I of f will be the number of critical points of f of index I, and we consider the difference of complementary indices. So mu I will be the number of critical points of index n minus I minus the number of critical points of index I. This goes into the structure result. And also we need some groups. One group will be the smooth-oriented cobordism group of manifolds, which is well known. Its definition is well known. And we will also require some torsion group, which only appears when n is of the form 1 mod 4. And then it has it takes the group z mod 2, otherwise it's 0. And we define the following invariant of a pair n, f, which takes values in this torsion group, which is only necessary to define if n is of the form that it's congruent 1 mod 4. So then we define it to be the following value mod 2, namely a certain sum of these new i's, and a second summand, which turns out to be nothing but the Kerber semi-characteristic with Q coefficients. So this term mod 2 is called the Kerber semi-characteristic. What you do, you add up the BT numbers of n up to the degree below the middle, because the dimension of m is 4k plus 1 in this case. So using these notions, there's the following theory of Ikegami from 2004. The case that n is 2 has previously been studied by Ikegami and Saiki, and an unoriented version by Kalman, which is not included here because we talk about oriented versions. And the theory states that the cobordism group of Morse functions is isomorphic to the following structure. The first summand is the cobordism group of manifolds, and then a certain number of direct z summands appears, and thirdly this torsion group Jn. And the isomorphism can be written down explicitly like this. So in the first component you just remember the manifold, the class of the manifold itself in the cobordism group, and then you extract those differences of indices for the z summands, and the last summand is just given by the invariant defined above.
In the line.
Yes.
And so here is hidden, the first line of the theorem, the formula. The dependence on f is hidden in number of summands.
Yes.
Because if I just look at the line as formula, I don't see the left-hand side depends on f and right-hand side not.
You mean the formula? This
right. No. I mean the first.
This one.
The formula, the first
this
formula.
One.
No.
Oh, yeah.
Just n is isomorphic to oriented cobordism plus z, and it doesn't depend on f, right?
Right. F is just an element, and f represents an element in Mn.
Yes.
You mean these ones?
Yeah. So if I read formally, it doesn't depend on f. The left-hand side depends and right-hand side no.
Sorry, I am confused.
Ни одна из частей не зависит от f. Слева множество всех классов эквивалентности. Справа какая-то группа.
Ah, okay.
But which side does not belong?
Одна группа в другую.
Okay.
Is it okay? Or?
Yeah, okay.
So this is just the isomorphism you get. And now I will show you a different approach to the structure of the group Mn, which takes a totally different perspective. So for this purpose, I have to talk about cutting and pasting relations. So let me define what this is. So given closed n manifolds x and y, we define a relation x is related to y as follows. We say x is related to y whenever you can write x like what you see on the left side here, and y like what you see on the right side here. What does it mean? On the left side, you write x as the disjoint union of two gluings of some manifolds with boundary along the common boundaries. The gluing diffeomorphisms we use are phi and psi. And if x can be written like this, we say it's related to y. If y arises like what is written on the right side, and you see the difference is just that we switched the gluing diffeomorphisms. So on the left side, we glue m and the oriented inverse of n prime along phi, and n and n prime along psi. And on the right side, we glue m and n prime along psi, and n and n prime along phi. So this in particular requires that the boundary of m and the boundary of m are equal, and the boundary of n prime and the boundary of n prime are equal. But this kind of relation is to be studied. This is called SKK relation. It comes from a German description, which means cutting and pasting in a controllable way. And this kind of relation has first been considered actually by Janich in work on index theory of elliptic operators, but a very nice write-up of the more general and more systematic theory can be found in the following manuscript, which is due to Karas, Keck, Neumann, and Osser from the 70s. And they studied this kind of relation. What can you do with this? It's not an equivalence relation, but you can define something. You start with the abelian semi group of diffeomorphism classes of closed oriented n manifolds. So you can add them by using the disjoint union. You can have an identity element, but you cannot subtract them. And we call two such classes SKK equivalent if you can stabilize by x and y in such a way that this equality holds and x is SKK related to y. And then it turns out that this construction is an equivalence relation, in fact. And so you can consider the quotient, which inherits a semi-group structure from what we started with. And if you take the Grothendieck group of this quotient, you end up with a group which is denoted by SKKN, and which is called the SKK group of manifolds in dimension n. So this is kind of completely unrelated to Morse theory, it seems. Okay, just to give you a quick impression, we don't have much time, but to see what happens if you take the torus, the two torus, you can show that it represents the neutral element in SKK2, because you can consider the following. Take x to be this two-sphere disjoint union with three other two spheres, and then you see on this side you switch the boundary circles, which turns the left part into a torus plus a sphere, and the same gluing diffeomorphism does nothing on those other spheres. So you see that 4 two spheres are SKK related to 1 2 torus plus also 4 two spheres. So this is what can happen in this kind of theory.
Excuse me?
Yeah.
Is it difficult to prove that when you factor you get a group?
When you factor
By this?
one?
Yeah, you take a group, right? It's written, Grothendieck group.
Yeah, right. So this one is just a semi-group. And then I take the Grothendieck group of this semi-group. Sorry.
The usual construction of...
Yeah. Maybe it's misunderstood.
Yeah.
But this, we take the Grothendieck group of this object, which is a semi-group. Yeah. Right. Okay. So there is a relation between cutting and pasting relations and the Cobordism group of Morse functions as follows. So consider again Morse functions f and the number of critical points of index I. And we also had the notation taking the difference of numbers of critical points like this. What we do now, we define an integer as follows. Given a pair m, f, we define an integer as follows. We take either this sum when n is odd or this sum when n is even. In the case that n is even, you have this blue term which appears, and sigma of m is the signature, which is only non-zero when the dimension of m is divisible by 4, so otherwise you plug in 0. And chi of m is the Euler characteristic. And in particular, the statement tells you that this should be an integer, otherwise it's not an integer. So this is what you have to check. And then the theorem is as follows. I can show that there's an isomorphism of groups. This is the Cobordism group of Morse functions on the left side. And you can find an isomorphism which is explicitly written here, which identifies it with the SKK group of manifolds and some direct Z-summons. And how is the isomorphism given explicitly? So a class represented by a Morse function f on m will be mapped to some element in the SKK group. Note, in this case, it's not just a class of m, but we need this integer and take the multiple of the class of the n sphere and have to add it to this class. And then we get a well-defined map into SKK and up to Cobordism of Morse functions. So this is one of the differences to the other formula I showed you before. And in the other summons, you just take those new i's that we define above. So this is an unexpected connection between the theory, or the Cobordism theory of Morse functions and what they call SKK groups of manifolds. And this can be helpful later. So this is one topic I wanted to talk about.
Excuse me, yes. Can you just join the previous result when you obtained mn and this one?
This, the previous?
The previous one of mn. So,
this one?
Yeah, so we can say something about connection of the component.
Yeah. So in particular, this Jn must be contained in the SKK group.
Yeah.
And the SKK group has also been understood, but this is completely unrelated to Morse theory. So this approach kind of helps you to figure out what kind of information is really to be understood from the perspective of Morse theory and can be studied without any Morse theory. And the SKK group can be studied without any Morse theory. So this summand here, this Jn, is in fact not related to the Morse theory directly, but you can go the way via the SKK groups to understand it. Okay. So the next topic I would like to talk about is the topic of index constraints. So far we have just considered Morse functions. Now I would like to consider a certain class of Morse functions, which I call K-constrained. And given K, I call a Morse function K-constrained if its indices of its critical points are contained in this set. So you see, we need, of course, definite indices 0 and n, but in between we only allow indices in this type of interval. So this kind of means that the manifold should be highly connected because it's symmetric to this interval. But it is not so clear how to define the Cobordism relation. But you can in fact define f0 should be k-constrained Cobordism to f1 if, again, you find a Cobordism in the sense I gave you before. So you mean a Cobordism W from n0 to n1 and a map, big F, that is a fold map, basically from f0 to f1. And now you impose the additional condition that all the fold indices or fold points of this fold map big F should also satisfy kind of the corresponding index constraint. And there is a notion of index for fold points, and the index condition looks like this. So if you use this kind of definition, then you get, again, a Cobordism group, this time of k-constrained Morse functions. And I would like to tell you something about it. First of all, the problem arises to compute the structure of this. I mean, the case we considered before was the case that k is 1. This has been understood by Ikigami, that's what I told you in the beginning. But the case of higher k might be interesting. And in fact, there is another theorem due to Skk from the beginning of the 2000s, and he showed that when k is big enough, I mean this just means that you forbid all the indefinite indices here. If k is big enough, then the resulting cobordism group M and K, which is now called the cobordism group of special generic functions, because Morse functions without any indefinite critical points will be called special generic functions, then this cobordism group turns out to be isomorphic to the group of homotopy n spheres, at least when the dimension is at least 6. So in that way, you can detect exotic spheres. I mean, these phenomena are high-dimensional phenomena arising in dimension 7 for the first time to be known, discovered by Milner. And these arise in this context, in this group M and K. So for big K, when K is bigger than this constant. So what happens in between? For K equals 1, we have just the cobordism group of Morse functions, and for K bigger, we are here. So we have just 1 minute left. So I will present you not the answer to this problem, which seems to be very complicated, but at least one application to exotic spheres, which is the result of mine, which gives you an impression of what happens here. So let me just say an exotic n-sphere is a smooth manifold, which is homeomorphic but not diffeomorphic to the standard sphere Sn. And let us consider this group here. So this is the K we consider, n-1/2. And we show that this group helps us to distinguish some concrete exotic n-spheres from other exotic spheres as follows. Suppose n is of this form, 4r+1, and then there is the family of so-called Kerber spheres of dimension n. So there is a unique Kerber sphere of dimension n in these dimensions, and it is known that this Kerber sphere is exotic, except for a finite number of exceptions. I think the case of 125 is still unknown, and the others turn out to be standard spheres. So let's say, what happens? This is the theory. If n is big enough, there is a bound of 237, and n is of this form, and is congruent to 13, not 16, then, given any oriented exotic n-sphere, we have the following equivalent statements. First states sigma is diffeomorphic to the Kerber sphere, and the second statement says sigma admits an n-1/2 constrained Morse function, such that this Morse function represents the 0 element in here. So this shows you that in between the extremal cases, K1 and K bigger than n-1/2, you have interesting phenomena to observe, but it is not clear how to compute these groups, and the hope is to use the SKK-relations to say more about these groups in the middle. So this is basically what I wanted to say. Thank you so much.
Questions or comments? Yes, please. Can we go a couple of pages back to the definition of K equals? Yeah, here. If K equals 1, what is the constraint?
So if K equals 1,
Yeah.
then you have no condition because all the indices are allowed.
So what? So.
And one person
Can you go back?
back or
Yeah, next.
Next.
Yeah. So what is this? What it is?
this is the first group I mentioned in the beginning, where you have just a cobordism group of Morse functions.
Yeah. If K equals 1, what is the proof here? When
Here?
It is, yeah, here.
Yeah, you have to compute the structure, but Ikigami did it. That's what I write here. Ikigami computed the structure.
But there is no constraint.
No, there is no constraint. But that's the definition we have.
There is some.
Да. А как точки каких индексов разрешаются?
Ну, вроде всех. Если k равно единице, то всех.
Ну, это значит, что он mn и вычислен.
Right, there is no constraint in case.
Показать, что они равны, это
So you go back to the original definition.
Его результат не в том, что равны, а в том, что он его вычислил.
What kind of answer is that without constraints for this MN?
Without constraints,
Yeah,
without
what's the result of the
this one here, or
Oh, yeah.
So this is just the special one extremal case. The other extremal case is the result of Skk, which
Equality is just to make that this is the same. That's all.
K greater than n minus 1, how many options for K is left?
So you have 2 until n minus 1 halves. And the case that it's n minus 1 halves is considered here. So this
There
is
are just 2 options. Yes.
2 options.
But K is greater than n minus 1
Halves.
half, then how many options for K are left?
No, if k is bigger than this, then you just have only definite folds. So
Last slot.
yeah, last
Last, yes.
this one.
Yes.
Some more questions?
Any more questions?
If not, sir, thanks. Okay.